Welcome, everyone, and thank you for coming to this talk. I'll be speaking about functional reactive programming paradigm as implemented in reactive extensions libraries such as RX.NET, RxJava, RxJS, and so on. There are lots of them. They're very similar. They share the same patterns and the design, and this design is what we're going to concentrate on. You might know this popular meme by Andrei Staltz. He's a very smart guy, and he wrote an essay where he let's say, convinces that everything we see, everything in our code could be represented as a stream. I would like to take this idea and push it one step further and find real-world examples, real-world metaphors of streams in the surrounding world. I believe that finding real-world metaphors is a very good way of learning new things, especially new paradigms. My name is Tomasz Ducin. I work as independent consultant. I do trainings mainly on JavaScript technologies, which includes JavaScript, TypeScript, Angular, React, and lots of other stuff, including RxJS. Also, I am a member of commercial project teams. So if you want to get in contact with me, feel free to do so. What we're going to speak about today is, first of all, streams. We're not going to talk about operators on Rx libraries because there are over 100 of them, and basically this is what we are having documentation for. So operators is something for documentation. We're going to focus on the fundamentals and the philosophy behind. So inversion of control and reactivity, the core concepts, managing subscriptions, and finally, one of the least understood topics, which is hot and cold observables. And I would like to explain why I find this harmful simplification by explaining different types of subjects. So let's talk about streams. Basically, every word I say to you is a stream. It's a sequence of words that I speak. Also, each of you that is coming to the room could be represented as a stream of participants coming here. Right? I would like us to open ourselves for creative thinking about our surrounding world and find streams here. From the code perspective, this is going to be one of the two slides that is presenting any code here. It seems to be pretty straightforward. At the top line, we've got a source of the stream. So basically, it's going to emit some values. Notify with some changes. There are some operators that alter the behavior of the stream, and finally there is a consumer or multiple consumers that would basically make use of the values available. An example is a currency rate stream, basically notifying that the rate of euro, American dollar, Polish zloty, and so on and so forth is changing. We can use simple operators such as map to get, let's say, euro value, then another operator to sample it. Basically, each 5 seconds, we're going to sample the value, no matter if what the frequency of the changes is, so whether it changes frequently or not. And finally, there is a subscriber. So it looks pretty easy, I think. How many of you have been using Rx in any language? Could you raise your hands, please? Okay, so I would say 1/3 of the room. And how many of you have heard about Rx at all? Okay, so most of the room, thank you. So I believe this should be pretty simple. So when learning streams, the first, let's say, thing to compare is actually an array. You could find lots of ideas like this in internet, just compare a stream to an array. The thing is, array has two limitations. First of them is, array has a strictly defined beginning and an end, right? And it's defined entirely upfront and available in RAM memory. It might seem pretty obvious, but it's not the case with the streams. So in streams, the values are becoming available over time, right? So it's not defined upfront. Also, if we take a look at the stream, we don't know whether we are expecting any new values to arrive, right? Unless the stream is completed, right? But there is no such thing as being completed with an array, because array is just strictly defined and available upfront. So this is a very big difference. Though we can think about a stream as an array that is growing in time, right? Important thing, array, when we think about arrays, is just data, right? When we think about streams, it's data and time. So we have multiple combinations of operations on data and operations on time. For instance, in JavaScript, we have, let's say, over 10 operators on arrays, and we have over 100 operations on streams, because there are so many combinations of all of it. Real-world metaphor of a collection growing in time could be TV news. At the bottom of the screen, we can see a stripe with news headlines that are just moving from one place to another. So there is one information, then another one, and so on and so forth. All right, technical difficulties. Is it better now? Okay, thank you. Right. A lot better way to think about streams is not to compare it to an array, but actually to a variable. Just the simplest variable you can think of. So a variable might have a value, and it changes over time, another value, and so on and so forth. So we could define a stream as a variable that changes its value over time, and it will notify everybody that is interested about the change, right? The thing is, if I'm going pull-based approach, so I'm checking whether the value has changed or not, I need to know when to do the check. But when we invert the control and go push-based, which is the reactive way, then I will get notified. I don't care when to check the value for the change, right? So replacing a variable with a stream is something that we will do a lot more often than replacing a collection that is growing in time. Also, very often, streams never complete in a program, right? Because we are expecting more data, we are expecting more user interactions, whether we are doing front-end or back-end. Also, variable is just data, right? We have a snapshot of the value. Only the snapshot, the current snapshot. And in streams, we have data and time. So we can see not only the values, but also the point in time when the values change, when they become available. A metaphor of what a stream representing a variable could be is currency exchange. Let's say we would like to convert Polish zlotys to euro, and we have a currency exchange rate. That's just a value that changes over time. The thing is, we could snapshot it in a variable, but we will not get the notifications about the change. The idea here is that if it's represented as a stream, it will notify automatically. There is a lot more about it, but we'll see it in a while. So let's talk about streams from a different perspective. If I'm looking at the news headlines, I am basically notified about all the stuff that is going on here. The thing is, if I turn my head around and look at something else, and I go back, there might be some headlines that I have missed, right? Because I am not controlling the speed, or I'm not controlling when do new items arrive, right? Let's take another example of a stream. I'm reading a book. So I'm reading a word, another word, and another word, and another word, a sentence, another sentence, and so on and so forth. If I move my head around, or I just take a break, whatever, and I get back to the book, I know where I finished, so I can just continue. Did I miss anything? No, because I control the speed. I control the flow of the data, right? So let's say that a book is a stream of words, a stream of sentences, and this TV is a stream of news headlines. This is push-based approach, so basically there is some engine, some item that will notify the events, and I'm not controlling the flow, I'm not controlling the speed when the new items arrive. If I don't subscribe to it, I miss them. However, this is pull-based approach, where the consumer is responsible for actually calling for the new items. So this is one of the most fundamental difference. In all languages, we have both push-based and pull-based approach. In JavaScript, for instance, pull-based is implemented as generators, as well as in .NET, and in Java, it's Java streams. So all languages might have different implementations of the same design, of the same pattern. So one of the most important questions to ask ourselves whether we should use Rx or not is basically, is it more convenient for us to have push-based approach in our code or pull-based? If I control getting new items, Is it more convenient for me, or would I prefer to push? For instance, if I go pull-based, I do have more responsibility, so it might be less convenient. On the other hand, if I go push-based, then it might happen that there are so many items incoming that it's just too much for me to catch up with them. So I need to handle backpressure. So either I will buffer them, or I will just drop some values. So there are pros and cons on both of them. One of the most fundamental thing about streams and lots of modern frameworks and tools is inversion of control. Let's break it down. Inversion of control, obviously, it's not only dependency injection. There is a lot more techniques of inversion of control out there. So what is inversion? First of all, there has to be some kind of flow. How do things work? Let's take an example. Some friend of mine writes me a letter, and a postman is expected to come to my door and deliver a letter to me. This is the default. There has to be a default always. However, if I'm not there, if I'm not at my flat, then the postman will leave a post notification. And now, instead of postman delivering a letter at my door, now I have to walk to the post office, right? So we have inverted the control. And in real world, it happens way too often in my country. So there has to be a default flow, which we will invert. Now, what might be a control? We need to define what is the control. So let's take a metaphor of driving a car. When we drive a car, we need to decide which gear is on. Do I step the brake pedal or gas pedal? Do I stop at yellow light? Should I slow down or speed up, right? Should I turn left or right, take this way or that way? So I need to make a lot of decisions about low-level details, a lot responsibility on low-level details. What I could do is basically to use a framework or use a service that would do the stuff for me, and it will take all the responsibility about low-level details, so I can just tell, take me to, let's say, the main train station, for instance, right, or to the airport, right? So from this point, I don't care about low-level details. I just tell what I need. It's like dependency injection. Just give me the instance. And I don't care about when do you create it. I don't care how do you guarantee that there is only one instance. I don't care about how do you share them, right? Or in React, I define only how the view should look like. I don't define when to update it, which part to update it. I don't care. I just define what it is. Inversion of control very often comes along with declarativeness. So basically, inversion of control is actually losing control. So I'm trading low-level responsibility on low-level details for, let's say, higher-level overview, where I can focus more on higher-level stuff, but I lose the control over low-level details. So let's speak about declarativeness as compared to imperative approach. Basically, our hardware is imperative. Imperative meaning we're doing orders. Please declare a variable, take a value of the variable, take another variable, add their values, and write it in another variable. So it's do an instruction, another instruction, another instruction, another instruction. This is low level, and we are responsible for all these kind of, let's say, hardware details, such as storing variables. Let's take an example. This is the easiest example I could think of where we might see what is declarativeness and what is reactivity about. So we have 3 variables here. It's about currency exchange again. We want to convert Polish zlotys to euro. So we have 3.94, the cost of €1, and we have 1,000 Polish zlotys. And basically, we want to calculate what is the value of the exchange. So in this case, we could get 253.80 euro for this kind of stuff. The thing is, the super important thing is, it's pretty fundamental code, but I believe this is really, it's really important. Here in this line, number 3, we have defined an invariant. Invariant meaning, at each point in time, the value of exchange has to reflect what is the value of amount divided by value of rate. This invariant has to be held. If it's not held, we have a bug, 100% bug, right? So if it happens that I change the value of rate, the value of exchange is not updated automatically. You could say, oh, this code is so simple, just overwrite value of exchange. Right, because this code snippet has 3 variables. But in our projects, it would not be 3 variables. It might be 300 variables, or more probably 3,000 variables, where it's not that obvious to find what are the invariants. The thing is, when we define streams, we will define the invariants, this logical dependency, natively. Everything will work out of the box. The nice thing about Rx is that it solves lots of bugs like this, and the cost is that the entry level is pretty high. We need to learn a lot. So a desync, or basically breaking the invariant, is something very, very bad. On the other hand, how we would define it in a declarative approach. This is a pseudocode. This is not, let's say, real code. We define a stream of rates. The initial value is 3.94. We define a stream of amounts. The initial value is 1,000 zlotys. And we define an exchange. As I said, this is a pseudocode. And we define that whenever amount or rate has a new value, the value of exchange will automatically update. So when I do 3.97, a new value available in the rate stream, the value of exchange will basically run this piece, right, and update us. This would be a real code in Rx. So I'm combining latest values of amount and rate, and when any of them is available, basically this function is going to be executed, right? So there is no way that I could get a desync between my variables. No way to break the invariant. This is really, really important. So updating value of any of them will basically propagate. We could say that it will downstream some new values that we would like to consume. So we are, from imperative to declarative, we are moving from what our code should do, from what it should do, into what it is. Instead of what you should do, instead of verbs, we define nouns. It's easier to grasp bigger pieces of code when we declare stuff without going into low-level details. So, cool thing about reactive streams is that they hold invariants natively. And that's all the catchy thing about reactivity. So let's speak about subscriptions. Once we have defined a source of data, we would like to consume it and make some actual practical use of it. So in this picture, the source of data is actually the headphones that this young man is wearing. I could wear the headphones and I could take them off. It means that the subscription is not something that will remain forever. I can activate the subscription, deactivate it. It can be turned on and turned off. So we have to manage the subscriptions. Also, we have to manage, so in this case, it's one subscription. Also, we have to manage the number of subscriptions. In this example, there is a timetable on an airport. It could be arrival flights, departure flights, or when we collect our luggage. It could be a luggage belt, whatever. But basically, people come to take a look at the timetable, and they walk away. So the number of subscribers could change. And the question now, this is an introduction to hot and cold observables. The question now is actually how many of the data sources are there? It turns out that by default in reactive extension libraries, each stream is called, so-called called, which means that for each subscriber there is going to be a separate producer created for them. This means that by default, if there is one person looking at this timetable, there is one timetable. If there is another person looking at the same timetable, there is another instance of the timetable being created automatically. When they unsubscribe, the timetables get destroyed. This is the default, which is obviously a great waste of resources. So we came to hot and cold. The reason I think hot and cold is a harmful simplification is that there is one type of cold observables. So basically, there is one producer for one subscriber. If we have 7 subscribers, we have 7 producers. But there is at least 8 different types of hot observables, which are completely different. They're really, really different. So instead of thinking about cold and hot, I would suggest thinking about Unicast and Multicast, which we will see in a while. By default, each Rx observable can only unicast. It means that a producer is able to supply a single subscriber, only one. If there is another subscriber, there would be a separate producer created for it, right? If you want to, this is obviously a waste of resources. If you want to share a producer among multiple subscribers, we have to use something that is called a subject. And by introducing a subject, we make a stream, let's say, hot, but actually what we do is we are multicasting the values. Instead of casting it to one single subscriber, we are casting it to multiple subscribers. So a subject, there are various different types of subjects, but a subject is just a proxy that is put between the producer, between this red dot, and between the subscribers that are marked as green here. So basically, the subject will subscribe to the source, it will hold the subscription, keep it alive, and when any value is available here in the producer, it will propagate it to all consumers. By default, Rx observables are not capable of doing it. There are reasons for it, including performance and basically having the code dry, don't repeat yourself, why they made this differentiation. But what we need to care about is make sure whether our stream is hot or cold. An example situation where you might fall into trouble, very popular one, writing code in Angular, using http.get in multiple places, you go into web console and you find that instead of doing one request, you are doing 7 requests because you are using the value in 7 different places because you didn't make the stream hot, and basically each consumer, each place you use the value is creating actually a different call, so we want to avoid it. So, to sum up, cold streams are unicasting. It means that for each subscriber there is a separate producer, so no sharing values. Hot streams means it's multicasting between all the subscribers and the producer is being shared. An example code with the subject. We're creating a subject with just Rx subject, and multiple subscribers can subscribe to the subject, and the subject itself can subscribe to multiple data sources. Right? So it doesn't have to be one producer, it could be multiple producers, but this sharing, bless you, this sharing takes place at this point. So let's make a small demo. I'm going to use my phone, which is a call observable, right? And when I'm making a call, only I can hear it if I just listen to what is going on here. But if I use this microport, and this is going to be a subject, I'm going to broadcast what is going on here to each of us.
Dzień dobry. Witam Państwa Trzeci Urząd Skarbowy Warszawa Śródmieście. Right. Zachęcamy Państwa do składania deklaracji podatkowych w formie...
So, basically, there is a single source of the data, and there are multiple subscribers. And we have to put a subject that will basically multicast the values here. So in terms of sharing, I said that there are 8 different types of hot streams out there. This is 2 strategies multiplied by 4 different types of subjects. Let's go through that. First, we need to publish, which means we need to put a specific type of subject in between the producer and the consumers. And ref count is a strategy that if I would do a talk, if I would do a lecture, I would not start speaking if the room was empty. So basically, if there is nobody listening to me, I won't start. If I was very eager to speak, I could do a connect, which means basically when I invoke the connect instruction, it doesn't matter how many people subscribe to me, how many of you listen to me, I would just start speaking, right? That's the difference. So ref count is basically keeping the connection alive if there is at least 1 subscriber, or if you pass any kind of number here, at least n subscribers, and connect is, I don't care, just go with it. So we have 2 strategies. This one, as you can imagine, is the most popular one, and hence it has an alias for it. And there are 4 types of subjects that we will go through. Subject, which is basically, if I'm listening, I get the value. If I'm not listening, I don't get the value. If I'm late, I don't get anything. Behavior value, I guarantee that there is one initial value available. Replay subject, there are, let's say, n last items that would be repeated if I come late. So basically, it's a replay. I can define what is the number here. And async subject, which is, I don't care about intermediate values. I only care about the final value. So it's similar to a promise, similar basically to the end value, the final value of whatever operation it is. So let's take a look at metaphors. Subjects, a subject is, if you're listening, you get it. If you don't listen at this point in time, you lose it, and you will never get it again. So it's basically, subjects are observables and observers. Observables because subscribers can listen to it, and observers because they subscribe to the source themselves. So theater is an example situation of a subject. We have an actor, this is the subject. We have a prompter that will prompt what is the script of the play to the actor, and we have the audience. The audience is subscribing to the actor. Whatever the prompter is suggesting, it will be, let's say, repeated by the actor. And let's take a look at a small demo here. So this actor is pretty lousy. He has forgotten his text. So he is like stammering what to say. And when the prompter will prompt some text, he starts speaking what is the script of Hamlet, whatever. But basically, the subject can invoke next, which means pushing the value into the subscribers, or it can also subscribe to any sources that are out there. If any member of the audience basically turns away and doesn't listen to it, he or she won't get the values that have been missed. So this was subject. 2 different types of subjects if you want to handle late subscription. First of them is behavior subject. We come late to a match. Or maybe we don't have to come late to a match. When we start watching a match, the result is 0-0. We are guaranteed an initial result. If we come late, let's say here it's Czech Republic 1, USA 0, then we are guaranteed what is the current value right now. So this is behavior subject. Another subject is replay subject. Tell me what were the last 3 goals. If the result is 0-0, there were no goals. If the result is 1-0, there is 1 goal, and so on and so forth. So here we are guaranteed in terms of behavior subject and replay subject, we are guaranteed values if we come late. And finally, the last subject is async subject. We don't care about what were the intermediate values. We only care about the final result of the whole operation. So we have an auction house. There is an auctioneer doing the auction, and here are people that will bid the values. So people will suggest, people will bid what are the values. The subject is subscribing to them, and there is a person somewhere in behind, a chief financial officer or a director, that doesn't care what were the intermediate bids. The director cares what were the final value that this painting was sold. So only when the stream, all of these streams complete, there are no more bids, this subject would also, the async subject, will also complete and notify the CFO or the financial director, whatever, about the final value that this painting was sold for. Also, when the CFO comes late, then this value will be available. So we have 1 type of called observables, but at least 8 built-in hot observable types. Ref count, at least 1. Connect, I'm speaking to a room and nobody is listening to me. And 4 different types of subjects, so 8 of them. So instead of halt and called, I suggest to think about multicast and unicast. So there is a lot more to speak about reactive streams. This is all I've got for you. Thank you very much.